Okay, in this video, we are going to take a look at polynomial functions. We're going to talk about using common differences to comprehend degree and use that knowledge to go to our calculator and determine the function that models a data set. Okay? So this video assumes that you have some comfort with a couple things. One is computing common differences in a data set. And two is that you know the definition of the degree of a polynomial, which if the polynomial is in fact a polynomial and it's written in general form, it is the largest exponent in the expression. Okay? So we're going to move forward with the assumption that you're pretty solid there and take a look at this where it says directions. Determine the degree of the polynomial used to model the given set. Then use your calculator to determine the equation of the function that models the data set. Okay? So, first thing we need to look at is this fact. We've studied this in class a little bit, and you should have this decently secured. And you should say that the order of the differences that is constant is equal to the degree of the polynomial that models the data set. So it means that if you are doing a analysis of the common differences, and you're doing the first order differences, and they're all constant, then the degree of the polynomial that fits that data set is 1. Similarly, if you were analyzing the second order differences, and they are constant, then the polynomial that models that data set will be of degree 2, which means it'll be quadratic, and then so forth and so on, up into where if the degree is 3, because the third order differences are constant, then it will be a cubic that models the data set. So we're going to use that information on these data sets here to do a little analysis and then go to our calculator and find an equation that fits the data. Okay, so we have a data set here, just x and y. And the first thing we see that we really like is that all the differences in the x values are 1, which makes doing this analysis much easier. Okay? So let's take a look here to start at what I'll call the first order differences. Okay, and I'll use my calculator to do some quick computing here. Differences, again, that can be computed by subtracting consecutive values sort of in the reverse direction of the chart. So 3.2 minus 0.8 gives me a difference of positive 2.4, and 7.2 minus 3.2 gives me a difference of 4. I could keep going, and I will in a moment, but I wanted to stop and show you that it's obvious here that this pattern is not of constant values. So I already know it's not going to be linear. So getting back to it, because I'll need to keep going. 12.8 minus 7.2 is a difference of 5.6. Okay? And 20 minus 12.8 is a difference of 7.2. Again, because these are not constant differences, we know that the degree is not equal to 1, and it is not a linear data set. So I'll continue on to the second order differences, which I'll change colors for. And 4 minus 2.4 is 1.6. 5.6 minus 4 is positive 1.6. And 7.2 minus 5.6 is, in fact, 1.6. So we do see that these differences are constant, which means the degree of the polynomial, which will model the data, will be of degree 2. And you need to know that that means it is called a quadratic. This is an essential word in understanding what we mean by degree 2. And I need that word as I go to my calculator. So I've saved a little time here on my calculator to show you how I'm going to do this. If you notice when I hit my stat button and hit edit, I've got the data set already listed in. So, okay, so doing that's pretty easy. And then I'm going to go to second stat plot and make sure that it's turned on so I can get a graph of the data. And then I'll hit zoom 9 and the data is graphed. Oh, I'm sorry. I had something in my calculator from a previous problem I just need to take out here, and I'll take that out. Okay? So I've got the graph of the data here. can see that it's a soft curve, which is not a shock because it's quadratic, which means this is a piece of a parabola. Okay, so from here now, I'm going to get my calculator to compute the equation of the quadratic that hits this data, or at least models it, but it's going to hit it all because these common differences guarantee that it's a perfectly modeled data set. So I'm going to hit Stat, right arrow for Calculate, scroll down to where my regressions are, starting at 4, which says linear, which we already said it's not. So go to 5, it says quadratic. Choose that one. Do second 1 to pull L1 in, comma, second 2 to pull L2 in, and then comma, vars, right arrow for function, hit function, and choose 1 out of the list. I accidentally have 2 commas here, excuse me. And then when I hit enter, the calculator does 2 things. It gives me the parameters of A, B, and C to make the equation, and it also moves the equation over to the graphing window. Now, obviously, there's some pieces here that I don't need because the plus 0x plus 0 makes no sense from a simplify standpoint. So I am, in fact, just going to write this answer as y equals 0.8 x squared. That is the polynomial function of degree 2 that models that data set. And we know that it is because when I hit graph, you can see that this parabola will hit all the points in that data set. We'll do another example. Okay? So to do that, I'm going to reset my calculator, second plus 712. Okay? And come over to this example here. And I notice here in this data set that, again, we see that the common differences of the x values are all 1, which is good. Okay? And then, just to keep color-coded here, I did the D1s in blue. So I'll do that. 0 minus 2.5 is negative 2.5. Negative 10.5 minus 0 is negative 10.5. Now, already I see that these are not common differences, so I know it's not linear. But I'll continue on. Negative 35, just go into my calculator to not make a sign mistake, minus negative 10.5 is a difference of negative 24.5, and then negative 79.5 minus negative 35 gives me a difference of negative 44.5. So again, paying attention to this fact, where it says the order of the differences that is constant is equal to the degree of the polynomial that models the data. Well, I do not have that D1 creates constant values. Therefore, I know that the degree is not 1 and the polynomial will not be linear. Okay? So, but I will continue on and try and observe the second order differences. So, again, with the help of my calculator, just to give some precision here amongst these decimals and these negative signs. Okay, I've got negative 10.5 minus negative 2.5, which is a difference of negative 8. Negative 24.5 minus negative 10.5, which is a difference of negative 14. Now I already see that this is not a constant set of values in the D2, so I know it's not going to be quadratic, but I do continue. And then we see that we've got negative 44.5 minus negative 24.5, and that gives me a difference of negative 20. But I do see a pattern emerging, but let's stay with this fact here. We see that the degree is not equal to 2, and it will not be a quadratic polynomial that models the data set. So, continuing on, another color here, I'll do this in pink. The third order differences. We see that negative 14 minus negative 8 gives me a difference of negative 6. Negative 20 minus negative 14 also gives me a difference of negative 6. Now, this is what we're looking for. We are seeing here that these differences are in fact constant. Even though there's only 2 of them, they are in fact constant still. So we have that the degree will be equal to 3 that models this data set, which means we are looking for a cubic function. So I'll now go to my graphing calculator, hit stat, edit, enter my x values of 1, 2, 3, 4, and 5. Okay, and then I'll a little more carefully enter 2.5, 0, negative 10.5, negative 35, and negative 79.5, and read them over to make sure I have them right. Okay? Again, you're not entering the differences in the calculator, you're entering the data, because the data set is what's getting modeled by the function, not the differences. Okay? The differences just give you the analysis. So, again, I'm going to do second stat plot, turn the plot on, and then hit zoom 9. Okay? If you notice here, this is a curve. It's going to be a cubic, and you'll see what we get when we do the regression. So I hit stat, right arrow, scroll down the number 6, which is a cubic regression, again based on the fact that I know the third order differences were constant, so it's degree 3. Its name is cubic, so you need to know the vocabulary so you can go to your calculator and pick out the right words in this list. Okay, so cubic regression, second 1 to get L1, comma, second 2 to get L2, comma, vars, right arrow for functions, and put that in function 1. Okay, so then I hit enter. The parameters come back of A, B, C, and D for the polynomial of third degree. And I will, in fact, copy that here and get y equals negative x cubed, I'll forgo the 1 just to simplify it, plus 2x squared minus 1.5x plus 3. That's a third order polynomial. Not uncommon for them to have 4 terms like that. It's third degree. Then I hit the graph button to show that that is the equation that, in fact, hits all of the data points. By looking at y equals, I get a little bit of funky stuff there, just some how the numbers were generated and then put over to my calculator, but those values are, in fact, the ones we see in this chart for the most part and for practical purposes. Okay, so that's pretty much it in a nutshell. The plan of attack is to use the differences in an analytical way to look for which order of the differences will be constant, equate that number to the degree of the polynomial, and then making sure that when we go to our calculator for the regression, you're picking the right regression. If you notice, your calculator will do linear, quadratic, cubic, quartic, and I think that's it. If I poked around, I might be able to find a way to do like a higher order polynomial regression. So feel free to watch again. Enjoy.